that, there's lots of different ways to create the same logic circuit. In this example, we did this using sum of products, and this one using product of sums. We talked about min terms and max terms that you use for the two different methods. We went over some more examples. We did an in-class example with a timing diagram. Started talking about binary number systems and adders. So any questions about anything we covered last lecture? Okay. All right. Well, then we'll move right on to the next thing we're going to talk about is Karnaugh maps. So last lecture we discussed. Give me one sec to. I've got it so that I can see the chat and give the presentation this time. So last lecture we talked about how to use the sum of products and product of sums method to find out how to make how to build logic circuits based on a truth table. Today I'm going to show you a much better method for doing that in a way that's a lot more efficient, and that's using Karnaugh maps. So what is a Karnaugh map? A Karnaugh map is a sort of a little table over here that corresponds to all of the different possible inputs, and you fill the table with what the outputs are. And so for a two-input circuit, this is what the Karnaugh map looks like. And you have a square for each one of the terms here. Okay, so for xy, where it's x is 0 and y is 0, that min term is here. For when x is 0 and y is 1, that term is here. For when x is 1 and y is 0, that term is here. And for x1, y1, that term is here. Okay, so how do you use this? So let's take this example. We've got 4 terms. For 0, 0, we've got 1. For 0, 1, we've got a 0. For 1, 0, we've got a 1. And then for the last term, 1, 1, we've got a 1. Okay? So what you do is you circle all of the spots where the output is 1. So we've circled here this section, and we've put a circle here for this section. And then what you do is you look at the spot that you've circled. So in this case, we're looking at this orange circle here. And the thing that is constant in this circle is 1. X being 1 is what doesn't change, okay? And so our first term here is simply X, or, and then for this term, the thing that doesn't change is not Y, okay? Or the spot where this is 0. And we can see here, not Y. So our function for this is X or not Y is equivalent to, that is the implementation for this logic table. So this is more condensed than if we literally went through each min term. And, remember that the method I showed last time where, you'd have X and not Y, or X and not Y, or X and Y. This is a much condensed version of that. So, this would be the usual way using the sum of products method. Like I showed last time, that's what it would look like. And you could optimize this by hand, right? So if you look at this logical equation, you could use one of the theorems we talked about last time to basically you would expand this. So this X and not Y, you can actually expand it and include it twice because of the idempotence theorem. Okay, so anything ORed with itself is still equal to itself. Okay, so you could add that, and then you can factor out the not x and y and the not y, excuse me, the not x or x and the not y or y. You could factor those out. And then you could use another theorem to just get rid of those entirely, right? So you could do this way using all the theorems and stuff. And, this is just sort of something I want you to be aware of. It's not, I might have you do one or two problems like this, but this isn't really this isn't the usual way to do it. The good way to do it is with Carnot maps. So any questions about any of that?
When doing the Carnot map, is the output already given, like before you start?
Yes, yeah. So before you work on the Carnot map, one of the things that you'll get here is, you'll get the output. That'll be something that's given, and then that goes into this table. Sometimes you'll just be given this table because you'll just be given the Carnot map because this is just equivalent to this. So yeah, of course, yeah, if you didn't have that, then it would just be an empty, just be an empty table. So yeah, you'll be given that. Any other questions? Okay.
Yeah.
Yeah, go ahead.
So what if instead of sum of products we want sorry. What if instead of sum of products we wanted to do product of sums?
You can do that. And I'll show you an example of doing it that way.
Right.
Essentially you would circle this instead, and then instead of doing instead of doing the and then oring it, you'd or and then and it, just like we did for product of sums before. I have a couple examples that go over that. But yeah, you can with Carnot maps you can do sum of products just as well as product of sums. Most of the examples I'm just going to show sum of products just for just to start with, but I'll show you a couple examples with product of sums. So that's a good question. Any other questions? Okay. All right, let's continue. So you can also have 3 variable Carnot maps. And there's sort of one little modification in here that you got to be aware of. So like before, you've got all your possible 8 inputs for a 3 input, or 8 terms for a 3 input function. And they map to the table like this. So we've got X and Y here, and then we've got Y and Z along this way. And the one thing you got to be aware of is it goes 0, 0, 0, 1, 1, 1, and then 1, 0. And this is what's called gray code. And essentially all gray code is only 1 bit at a time can change. And so, for example, 0, 0 to 0, 1, only 1 bit is changing. From 0, 1 to 1, 1, again, only 1 bit is changing. And then when you go from 1, 1 to 1, 0, only 1 bit is changing. So that's sort of the only modification you got to be aware of. Usually, I think usually when the Carnot map is printed, you'll see this. You'll see that this is 1, 1. So just you got to keep that in mind. So let's go ahead and do an example. So first example here, we want to circle all. The rules are you want to circle the largest section that you can using powers of 2. That's sort of the fundamental rule here. So we're going to go ahead and circle that. And then we will circle down here. And then for this first term, the way that we arrive at this is x is always 0 here. So we've got x 0. So not x and not y, because that's the thing that's constant here. If you look at y is 0 over here, and y is 0 over here. So you have not x and not y. And then for the next term, you OR it, and then you've got, for that, you've got x is 1, okay? So it's a positive logic for x. And then for z, Z is 1 is also held constant there. And so that's the X and Z is your second term. So any questions about that? It's pretty much the same thing. It's just we've added one more dimension. Okay. So let's do another example of a 3-variable kernel map. So like I said, the circled sets should be as large as possible. You want to do them in powers of 2. So here we've circled 4 of them. And then over here, we've circled 2. So for this first term, or for this first set, I should say, X is positive for the whole thing. So, and the rest are changing. So this is simply X. Does anybody want to go ahead and tell me what should this next set be?
Y, not Z.
Yes, exactly. So it would be Y and not Z. So, and again, that's arrived at by, you've got Y here is 1, Z is a 0, and X is changing, so X is not included. And so, yeah, Y and not Z. So here's a 3-input a K-map. What's the first thing that we should circle here?
Top three. The 3 ones.
So they've got to be, one of the rules is they got to be in powers of 2. I see in the chat, Paul said the 2 by 2 in the middle. So yeah, anytime you've got 4 ones in a square pattern, those are the ones that should be circled. So, okay, we'll circle that. What are the next things we should circle? The singles. So what you want to do is you want to circle the largest thing that you can, even if they overlap. So you'll get a smaller logic function that way. So yeah, the Maroon said and Mahum both said, yeah, you want to circle the pairs here. So we'll circle there and we'll circle there. And so then what will our what would the first set look like here for blue? What should we write down?
Not X and not Y.
That's exactly right. Not X and not Y. And then what about for green?
Z.
Z.
Yep, that's just Z. And then for the last one?
X and Y.
Exactly. Yep, X, Y. Yeah, see, these are pretty straightforward. Once you, it's kind of like, they're kind of like little puzzles. So, you know, once you know the rules of the game, they're really not that bad. So here's another one. Now there's one sort of thing that you should be aware of is that the first column and the last column, they wrap around and connect. Okay, and so this leftmost column is considered adjacent, to the rightmost column. And so if you are in a case like this, you actually your circle will wrap around to the other side. And then this one you circle just like normal. So what would that first blue term be?
Would it be not X and not Z?
Exactly right. Yep, not X and not Z. And then you know, the next term would just be X and Z. So so there we go. All right, let's work on this one. So what should we circle for this?
Should we do
Quad.
the box first? The square?
Yep. Yeah, we'll do the square, and then what about, I see in the chat there, 2 squares. Yep, exactly. And remember, they can wrap around, and you want to make the sets as large as possible using powers of 2. So these are the largest possible sets, and so I already clicked ahead. The first one is not Z, and we arrive at that because X is changing. We got both 0 and 1. Z is what's constant here, the not Z term, and then somebody want to go ahead and tell me what should we do for orange?
Why?
Yep, exactly. Why? So yeah, those are three variable K maps. You can go even farther. You can extend them to 4 variables. Before I jump to that, any questions about any of the 2 and 3 variable Carnot maps that we went through? Okay, good. Let me ask you guys, did you guys do this in ECE 2400?
Yeah.
Okay, good. All right. So this should just be a review. But it's good, if you had the 2400, maybe you had it a year or two ago, or, that was, maybe, I don't know if you guys had that last semester or whatever, but it's good to get a review and sort of freshen up with this stuff. And so you can also have 4 variable K maps. Again, you want to be aware of the order here. So we have to follow gray code along these sides, 0, 0, 0, 1, 1, 1, 1, 0 along both sides. And so the order is a little modified. So we'll go ahead and let's do a 4 variable K-map example. So what are some of the things we should circle here?
The
squares.
Yep, we want a square in the center, and I've got this in a different order, so I'll just go ahead and click through. You want there's a couple different ways to do it, you'll find, but this is sort of the most optimal way, okay? And I'll explain why that is. So the 2 kind of rules are, you want to do the largest circle that you can, and you want to do as few circles as possible, okay? And so in the rules in that order. And so if we want to circle right across here, these 4, we want to grab this one here, and then we'll grab this and this. You could, now you see, if you put, I'd have to think about this here. If you had put this circle here, you would have actually needed another, I think you would have needed a 5th circle to grab this straggler. And so I believe this is the most efficient way to do this one. But if you did it the other way, they should get you the same answer. The only question is, how many logic gates are you going to use? And so by making the circles as big as possible, you make the most efficient circuit. So
is it possible to use a rectangle for like 60 lines?
Like you're saying, let's say this square here were populated. Could you do a rectangle around there? Yeah, I don't see why not. Yeah, I believe you can do a rectangle.
No, I think he's asking if you could do a rectangle around the 2x3.
Oh, I see. No, you can't do that. It's got to be powers of 2. So, yeah, you could do 8, but you couldn't do 6. So, generally, for all the problems, they're going to sort of look like this, where you've either got a long 4 here, or a little you're either circling 2, 4, or 8. Really. So, okay. So let's go ahead here. What should we write down for blue?
It would be not W and Y and not Z.
Exactly. Yep. Not W, Y, and Z. And then or with we'll do orange next. What would we have for orange?
Not W, not W and X.
Yep, exactly. You guys are good at this. And then what about for green?
X and Y.
Yep, exactly, X and Y. And then what about the last gray set there?
W, not Y and Z. Yeah.
Exactly. Yep. W, not Y, and Z. We'll do another one. You guys seem pretty good. You guys seem pretty good at this. It looks like you've had it in. Sounded like you had it in 2400. This is a tricky one. Actually, I'll ask. Does anybody know what do we do in this case? And again, remember. Yes, exactly. Square in the corners. So that's exactly right. So we would do that. And then we would take care of the 4 and the 2 there. And so for the square in the corners, the term or the inputs that are constant are X, or excuse me, not X, and not Z. So that's what we'd have for blue. Then for orange, we would have W, X, and then Y is also constant there. And then for green, we would have not W and Z. And that's our the other 4 variable K-map. So these examples that we went through pretty much cover all the kind of things you'll see with K-maps. So, we went over 2 variable, we went over 3 variable, we showed that, you should make the sets as large as possible. You can have squares as well as long pieces. And then remember, they can wrap around. And they can wrap around, you can wrap a square around too. And then we showed some 4 variable K-maps, and we showed how it can wrap around in the corner in one case. So, okay. So let's talk about like a real world example using Carnot maps. Just grab my water here. Okay. All right. So here's a real world example. This is what's called a majority gate. In a lot of really important types of systems that need to be really high reliability and you like literally cannot have a problem with it, they'll employ a method like this. So I'm thinking of like an airplane or a satellite, or in some parts of your car, you need to have a circuit that works every time, and errors are not acceptable. And so one of the techniques that they do for this is it's called triple modular redundancy. So you'll have 3 different modules, and these might be, for example, in an airplane, they might be in 3 different parts of the airplane, or they might be 3 different kinds of sensors that give the same kind of answer. So for example, these might be like 3 different altimeters that are in different parts of the airplane, and they use different methods, for example. And the idea with this is they sort of vote on what the right answer would be. And so if one of your altimeters goes bad, you've still got 2 that are working, and you can get the right answer. And so this is used, there are specific chips, for example, specific CPUs that actually have sets of 3 cores, and they all do the same operation, and they sort of vote on what the right answer would be. There's one there's a company called Infineon. They make something called the Tri-Core, for example, that's very common in automotive. And the idea here is that, things can randomly just mess up. So, a cosmic ray can come down and hit the transistor just right, and it will like flip from a 0 to a 1, for example. Or in the case of the airplane, where the modules are all distributed through the airplane, well, like one altimeter can just go bad. I mean, things just go bad. And so this is an example of a way to have something that's fault tolerant. So we got 3 different modules here, and just in this simple example, we're going to say like the output of the module is either going to be true or false. And so maybe this is for example, we'll use the altimeter example. Are we above a certain altitude or not? Just a binary yes, no, just as a very simple kind of example. And then the majority gate will, in this example, we'll look at all of the different inputs and decide, okay, what is the most likely output given this? So what would the truth table for this look like? So if all three are 0, then the output is 0. They all agree. If 2 of them are 0 and 1 of them is 1, then, well, this one must be faulty. So we're going to go on the majority and say that it's 0. Similarly for term 2, we got 2 zeros, and so the output will be 0. And then we've got 0, 1, 1, and so we figure it's a 1. 1, 0, 0, we figure that's a 0. And then for all the rest, we've got 2 1s, 2 1s, 3 1s. These are all, we'll say that the output is 1, okay? And so this is what the Carnot map looks like for that. And so to go ahead and implement a circuit that does this, we'll first, go through and do our circles. So we'll put a circle around there, circle around there, circle around there. And then we get, for blue, we get X and Z, or Y and Z, or X and Y, just like that. And so, and actually, after we've done this, this is sort of intuitively actually sounds like the right answer, right? So the output is true if X and Z are true, or if Y and Z are true, or if X and Y are true. So makes sense intuitively. And then this is what the circuit would look like. So, we've got our first gate here, X and Z, and then we've got our second gate here, Y and Z, and then we've got our last gate here, we've got, that was right. We've got Y and Z, and then we've got our last gate here, X and Y. And then we OR them all together. We've got just a 3-input OR gate, and there's our output. So this is a simple real world example of we had an idea for the system we wanted to implement. We wrote out a truth table. We did the Carnot map, and then we got the gates. And so this sort of an example is exactly what this might be a problem on a homework or on the exam. So we'll sort of describe a system, go to truth, make a truth table, make a Carnot map, and then make a circuit out of it. So any questions about this example? Okay, cool. So for a lot more Carnot map examples, if you still need some review, there's a great YouTube video here. And he goes through it's like half an hour long, and he goes through a ton of Carnot map examples. So if you're still feeling rusty on it, or if you're going through the homework and you're stuck, doesn't click in, this guy is great. So you can go through and watch some more. One question we had was, actually we'll kind of scroll back here. So we did a Carnot map with. Actually, yeah, it was here. We've been doing this with a sum of products, right? And so where a sum is a logical sum is considered an OR, and a logical product is considered an AND. You can also do it the opposite way. You could circle these zeros, and then it would be ANDed together ORs instead of OR together ANDs. And I have an example up on, if you go to Moodle, go ahead and pull this up for you guys. So here's our Moodle page. If you go to, so if you look under supplemental material, essentially what I've done here is, when I'm going through and coming up with the slides for this class, these are the books I'm looking at. And so if you want more information about this stuff, you can just sort of go right, this is sort of where I am getting things from. And if you go to this one, Carnot Maps and Logic Design, this, again, if you're still, or if you want to just sort of learn more about it, you want some more examples to go through, I've got a few pages in here about all the rules for Carnot maps. And so, he talks about how, yeah, you could do these as just individual circles, but it's not quite as efficient. Shows how they wrap around. And one thing that there's a few examples in here about is, all of these are sum of products, but you can also do product of sums. And so you can circle the zeros, and it's essentially just, it's the same thing, but in reverse. So for example, for here, rather than it being, so these are these right here, two different ways to get the same thing, right? So here you've got sum of products like we had been going over, and the ones are circled. And then here you've got product of sums and the zeros are circled. And so I went over product of sum, or excuse me, I went over
I have a
sum of
question.
products. Yes, go ahead.
So you circled just one there. I thought you had to circle in like pairs of twos, or could you do like 2 to the 0 is so you can circle one?
Exactly. 2 to the 0 is 1, and so you're allowed to circle a 1.
Okay.
And actually that's a good, I didn't have that in any of my examples or in the slides, but yeah, if you really have no choice and there's just a straggler here on its own, then yeah, you just got to circle that 1. But you always want to make sure that if you can circle 2, circle 2. But yeah, they're in powers of 2, 2 to the 0, 1, 2 to the 1, 2, 2 to the 2, 4, 2 to the 3, 8. So yeah, there's more examples in here. So as you're going through the homework or as you're preparing for the test, you can look at the examples in here as well to help you. So we've got that up on Moodle. And again, what I've sort of chosen to do for this class is rather than making you buy a book, you already have to buy a board. So I sort of just take the best from, I don't know, I've got like a couple dozen different electrical engineering textbooks on my shelf, and a lot of them cover the same stuff. So I just kind of grab snippets. What I did is I looked at how they all described it, and I chose the one I thought was, hey, these guys did the best way of describing it. So we'll go ahead and put that up on Moodle. So, okay. All right. So that's Carnot maps. Hopefully a review for most of you. But if not, there's if this is your first time seeing Carnot maps, I've got lots of resources for you to really get up to speed on them. So, okay. So now let's go and talk about, if we look at these, so for example, there's our majority gate again. Let's say we wanted to actually implement this physically. So how would we go about doing that? So let's go and open up the next set of slides. So this is, we're now going to be talking about implementing digital circuits. So the first sort of early computers used just literally relays. So a relay, remember, is a switch that's controlled electrically. And so this would literally be there's literally a coil, a little electromagnet there that is moving a switch back and forth. And so, these use lots of power, but they were that was the best technology they had at the time. Later, they came up with vacuum tubes, which achieved this within a tube and with there's a couple different variants on it, but it was ionized gas in some cases. But those, of course, had their problems too. They were, they use a lot of power. They have to heat up, that sort of thing. And then later on, like in the 50s, they discovered transistors. And in particular, as transistors developed, they identified, you can have basically a high side transistor and a low side transistor, and it's implemented with NPN or PNP junctions within the silicon. You'll learn obviously a lot more about this in your classes on semiconductors, but for just suffice it to say, for this class, we're going to be talking about an NMOS transistor and a PMOS transistor. And so these, you can, if you simplify it, you can just sort of think of these like they're switches. It's more complicated than that, but for this discussion, we can just think about them like they're switches, right? So, relays you can design so that they're either normally open or normally closed. And so a normally open relay, it's just, in this example, A and B, they're, the switch is open, and then you put a current through here, and they'll close. That's normally open. Normally closed would be, it's usually closed, and then the relay, the coil pulls it open, okay? You can do that. You have the same thing with transistors. And so this NMOS transistor, A and B are closed when C is logic 1, normally open. And then for PMOS, these are normally closed, and then when you put a 0 here, they will go ahead and open. And so, any questions about that? Okay, so you can take these switches then and build logic gates out of them. And so here, for example, is a NOT gate, and a NOT, it just inverts whatever the input is. And so for this example, we have a PMOS transistor here on the top, and then we've got an NMOS here on the bottom. And they're arranged in what's called complementary metal oxide semiconductor, or CMOS. And so what this is there are, on the high side, you've got your PMOS transistors, and on the bottom side, you've got your NMOS transistors, and they're sort of balanced. And the way that the logic works out, they'll do a particular logic function. And so let's say we have a 0 here. So we have a 0 here. This MOSFET is closed. And let me see if I can draw on here. Yeah, there we go. So when you have a 0 here, this MOSFET is closed, and so current flows through here, and then you've got a logic 1 on the output. Over here, when we've got a 1 here, this is open, but this gets closed, and so it connects the output right to ground. So does that make sense? All right. So you can make other kinds of gates too. So for example, we've got a NAND gate here. And let's look at this case. If we've got a 1 coming into both of these, so 1 goes here, this is connected, or this is closed, and this is closed. And so this is connected here to ground, okay? And I think if I hit escape, it'll discard. Oh, whoops. Sorry about that. I'm trying to figure out how to clear it. Oh, there's some tools down here. Okay. So now, if either of these are 0, what'll happen is, so for example, let's say we've got a 0 here, we've got a 1 here. So this is 0. So this is this becomes closed, and then that completes the circuit here. This is open, and so this is not closed, and so we've got a logic level 1. And then same thing for the other cases where we have at least 1 0. So does that make sense to everybody? So then similarly here for NOR, let's say we've got 2 zeros. So if we have a 0 here, this is closed, this is closed, and so the output is connected to 5 volts. Let's see, erase a link. There we go. And then if we'll take this example. So if X is 0, this is closed. However, if Y is 1, then this remains open. And let's see, Y is 1, and so this becomes closed, and so the output is connected right to ground. And so with this way, we can implement AND, we can implement NOR. How would we go ahead then and implement, let's say we wanted to implement an AND, let's say we wanted to implement AND and OR gates. How would we do that? So you might be tempted to think that you could interchange the NMOS and PMOS in the previous slide. So, you might think that, so for example, we'll look at an AND gate. You might think, well, hey, let's make this let's just make this an NMOS, and then let's make this a PMOS, right? And then that should be like an OR gate. So let's like try that, right? So let's say, so an OR gate would be if either one of them is a 1, it should be 1. So let's say we had a 0 and a 1 here. So this is 0, this would be open, but this would be closed. Okay, and then if we have a 1 here, then this would be closed. And then, hey, that should be logic 1, right? Well, due to the way that transistors work, you can't have an NMOS on the high side. And you can't have PMOS here on the low side. And it has to do with the rules about, like, in order for this to work as a switch, there's a certain relationship between the gate and the drain and the source that you have to adhere to. And that does not work when you have NMOS on the top and PMOS on the bottom. And so I have a little note here, remember that NMOS should always be on the low side, and then PMOS should always be on the high side. So the way that they actually do it is you take an AND gate, you throw a NOT at the end, and then that is how you get back to AND. So, the rules are PMOS here on the high side, NMOS here on the low side. Otherwise, it won't work. So, any questions about that? So, one problem, for example, that I may give on the homework or on a test is, hey, here's for example, I'll give you the symbols for this and this, NMOS and PMOS, and I might have you go ahead and make an AND gate or make an OR gate or make a NOR gate. So PMOS is closed when its logic is 0. Yes, exactly. So with the little bubble here, that is a PMOS. You can kind of remember that like P, it's a bubble. And then down here is NMOS. You can also remember it P, positive, high side, and negative, low side. Okay. Any questions about that? Yeah, you said PMOS logic is closed when it's logic 0. Yes, yeah. I should have actually pointed over to this one. So yeah, this is 0, and so kind of goes like that. Actually, a good slide to answer your question would be here. PMOS transistor, it's got the circle here, closed when the gate is 0. So, okay. So that's how you make logic gates using CMOS. So as things evolved, things originally, were just relays, and then we had vacuum tubes, and then we had some of the early transistors, and then we had, what they did is they started packing a bunch of transistors into a single integrated circuit. And so the 7400 series were some of the first integrated circuits ever made. And they all had these numbers here describing the part number. And so there was a chip here, and these last few pins here were sort of for your power supply. They're not labeled on here, but I think it was like your positive would be over here, your negative would be over here, maybe vice versa. But these chips would have these be little dip chips. You could stick them in a breadboard or in a printed circuit board, and these would have all sorts of logic gates in there. So we've got our 3 basic gates that you can make anything out of. You have inverters, a bunch of AND gates and a bunch of OR gates, all there integrated into one chip. Of course, as things evolved, things became more and more and more integrated, and now you've got like billions of transistors on a single chip for modern CPUs. So, but these were early days, and you can still buy these, because for a lot of little projects or a lot of places, all you might need is just maybe you just need a little multi-input AND gate. So for like let's say it's trying to think of a good example. You might want, for example, you might want to know on your circuit. Let's say you have a circuit and your circuit requires 3 different power supplies. Okay, maybe you have a 5 volt, a 12 volt, and a 24 volt, and you want to make sure that your processor only starts, or your circuit only starts when all of those power supplies come online. Well, one way of doing that really simply is you get a comparator, and you would use the comparator to find out, okay, have I reached the right voltage on each of the 3 power supplies? And you can take those 3 comparator pins and run them into an AND gate and see, okay, hey, are all of them connected? Are all of them high? And then you'd know, okay, all of my power supplies are available. Just as a simple example. There's other ways to implement that too. Some comparators have an output that is an open drain output, so you can actually just sort of tie them all together and get a common output. But that's just sort of one example. So a lot of times that's all the logic that you need. But for several years, this was all we had in terms of integrated circuits. They made, there's a whole, somewhere here I actually have a book. There's like thousands of different kinds, or maybe hundreds of different kinds of 7400 series integrated circuits. And they started packing more and more into these. Some of the, there was a 7400 series, and then later there was like a 74,000 series. And you can get like all the kinds of things that we're going to talk about later in this class, like muxes and counters and registers and shift registers and all that stuff. They started putting into these chips. So now one thing that's really interesting here is, so let's take, for example, like these NAND gates. We've got our 8 input NAND gates, or we've got our 2 input NAND gates. One thing that's interesting here, and this is arrived at through all those like identities and all the Boolean algebra theory and stuff. They basically they've arrived at the fact that NAND is a universal gate, and you can actually make any kind of gate just by wiring together a bunch of NAND gates. So for example, if all you have is NAND gates, you're stuck on a desert island with NAND gates, you can make any kind of gate. So like a NOT gate, all it is a, if you tie the 2 inputs together, it's equivalent to a NAND gate, or a NOT gate. Similarly for AND, you can, if you take a NAND gate, you NOT the output using this trick above here, and it's equivalent to just having an AND gate. And if you remember De Morgan's theorem, if you NOT before a, you can go between AND and OR by NOTing the inputs. And so that's what they've done here. And then you can, similarly, you can make a NOR gate, XOR, XNOR gate. I won't go through all the details, but you can make it just by tying them together. Any questions about this? So for example, on the homework, I might give that example where, hey, you only have NAND gates and you got to go and implement a circuit that way. Okay. Similarly, you can do the same thing, You can do the same thing with NOR gates. So NOR also has the same property of, if you tie the inputs together, you can make a NOT gate. Similarly, you can build a NOR gate that way. You can build an OR gate that way, and then you can build an AND gate that way, and then you can get to NAND and XOR, XNOR, and XOR in the same way. So NOR is also considered functionally complete. So that's kind of cool. So why is this important? So when they were first making semiconductors, if you're manufacturing anything, let's say you had to build a big computer, it's really hard. You can make one of something, relatively easily. But once you start trying to make, you know, a dozen, 100, 1,000, tens of thousands of something, it's very difficult to make sure that every single one of them is built and works every time. And so in the early days of integrated circuits, they chose to say, hey, okay, we're going to just focus on making, for example, NOR gates, and we're going to make a bunch of them because, you know, if we have to make OR gates and NOR gates and NAND gates, like it's much easier if we're going to make like, you know, 50,000 integrated circuits. Let's start off, let's just make one kind of integrated circuit for the most part. And then it's easier to test. It's easier to get your process just right. And so in the early days, that's what they did. And if you wanted to build something else out of your NOR gates, you just sort of would wire them together. And you'd get a higher, by doing it that way, you get higher quality. So in the early days of integrated circuits, one of the, can anybody guess like what was one of the biggest customers, let's say, you know, between the years of 1960 and 1969, what was one of the biggest customers, probably the biggest individual customer of integrated circuits? NASA, exactly, yes. And yes, calculators, it was in the chat. And essentially, this is just one of the most important and historically significant calculators ever. And it was the Apollo guidance computer. And so this is what allowed us to travel to the moon and back. And this is what it looked like. This is a little a keypad here, and it ran a very specific a computer program that allowed them to calculate their trajectory and how long they should burn the engine and all that sort of stuff. And it was built using a bunch of integrated circuits, and they were all, or not all of them, but the vast majority of them were dual 3-input NOR gates. And they took advantage of the same little trick that we talked about, that you can make anything out of NOR gates. And so there were 2,800 ICs, mostly 3-input NORs, in the guidance computer. And throughout the 60s, they ate up the lion's share of all the integrated circuits made in the United States went into Apollo guidance computers. I think the highest percentage was 1963, just over 60% of all the integrated circuits in the US. And keep in mind, like, the only people making integrated circuits at the time were pretty much the US and the UK. So this was, you know, close to at least a plurality of all of the integrated circuits made in the entire world went into, you know, the dozen or so computers for this Apollo mission. Now, they had other kinds of computers, you know, they had other kinds of, why NOR over NAND? You know, that's a good question. I'm not sure. There probably was a, if I had to guess, there was a, in whatever process that they were using, it either used more power or it was cheaper to go with NOR instead of NAND. And that might have to do with, I'm sure if you looked on Wikipedia or whatever, you know, they've got a good article here on the Apollo guidance computer. You'd probably find that out, why they chose NOR instead of NAND. So, you know, while you can achieve both, you know, the same logic with NOR and NAND, you know, they probably did an analysis and they said, well, you know, it would consume a little bit based on the way and based on the kind of logic gates that we need. You know, they maybe sat down and said, oh, we need, you know, 200 OR gates, we need 500 AND gates, we need, you know, they had a idea of what kind of gates they needed. They said, okay, we got NOR, we got NAND, and hey, we can save a little bit more if we pick NOR over NAND. Because they both are logically, will give the same output, but based on either the manufacturing process or like just the type of the mix of logic that they needed, I'm guessing that's why they chose NOR. So, but you know, somebody can look that up and maybe find that out. So yeah, this was huge. Okay, if you look at the timeline of history here, from, you know, during the 60s, at the beginning, towards the beginning of the 60s, these things were $115 each. Okay. And by the end of the Apollo missions, these went down in cost like almost 100 times. And now you're at like $1.58 a chip. Keep in mind, this is like in 60s dollars, okay? So this is like crazy. Whoops, let me clear. Yeah, so this is like a crazy drop. So, and then if you as you continue and you look through history, in the 70s, right after all of this, you had some of the first personal computers, the Altair and the Apple One, and you had the IBM PCs, and all of that was in the following decade. And so, a lot of people think about and talk about, oh, why did we go to the moon? What was the point of that? What's the point of NASA? If we hadn't done that, if we hadn't chosen to go to the moon, we would be a generation behind in terms of technology. You probably wouldn't be watching this on Google Meet right now, because your computer would be like a potato compared to what it is now. So by setting a goal for ourselves and going and doing it, and by NASA effectively subsidizing the semiconductor industry for an entire decade, that led to the whole growth of personal computers, and it led to because a lot of these companies were in Silicon Valley, and it led to the companies that made these ICs originally, and then it led to the whole computer revolution. And so that's just one of the things that we can thank NASA and the space program for. If you're curious about more, there's a really good Wikipedia article about NASA spin-off technologies, about all the sort of stuff that we got out of NASA, and the Apollo program, and the shuttle, and the International Space Station, and all the different probes. So it's pretty significant here. Okay, so that's just one of, I think, the most historically significant examples of some of the early applications of digital logic. Yeah, in the chat, Olivia pointed out, for reference, $115 then is about $1,000 now, right? So that's a pretty going by that, maybe this is kind of in the neighborhood of $10 roughly. So going down in price 100 times, pretty significant. So okay, let's continue on here and talk about programmable logic devices. And so let's say you have just sort of for clarification, excuse me, they started building after Apollo, and all throughout the 70s, they started building some of the first processors. You had the Intel 8000 series, 8080, 8088 series. You had Motorola, you had MOS Semiconductor with the 6502, which is like the CPU they use in the NES, and Apple II. And those they built using whatever gates they needed, they were able to just sort of implement right directly in silicon. But there were a lot of places where you're just making 10 of something, or you're just somebody tinkering with stuff, and you need you want to have a particular logic gate. You can't go and make what's called an ASIC, application-specific integrated circuit, like a processor or like a whole actual chip on your own. You'd have to kind of make it with either a bunch of TTL gates, or they started making devices called programmable logic devices. And what this would be is, this is a real simple example. Are PLDs the same as programmable logic controllers? No, they're different. So PLCs are these controllers that are used for specific industrial processes, and they're programmed in, I haven't worked directly with them, but I know they're programmed like ladder logic and a couple other kind of schemes. This is different. These are programmable logic devices. And the way that they work is, so for example, this is a real simple 2 input, 1 output PLD. And as I describe it, it should look, pretty familiar. You've got X and Y coming in, and you generate, you've got your X, and then you've got your not X, and then you've got your Y, and then you've got your not Y with these inverters here. And then over here, we've got some AND gates, and then we've got an OR gate. And so this is essentially doing product of sums, right? Because you've got your and here, which is your product. You got your and then you've got your or, product of sums here. And so you can, using little jumpers just for this simple example, you could connect these and make any kind of logic output that you wanted using these two inputs. And so, for example, I had some slides in there that were supposed to show that. Maybe they got moved around. Let's see here. I had some slides that showed that. Oh, you know what? Let me pull them up over here. Give me one sec. Okay, so this is from one of the textbooks. So for example, if you wanted to make an XOR gate, you could wire things up this way with these jumpers. And if you wanted to make an AND gate, you could wire things up this way. And similarly for an OR gate. Basically, essentially, what you're kind of putting here is you're kind of filling this in with your truth table, right? So that is that's what a PLD is. So let's go ahead and go back to where we were. Any questions about how this works? It's basically just a physical realization of the product of sums method that we've already been doing. So they started then making much bigger PLDs, and so this is, they just call it a CPLD, a complex programmable logic device. And this they still make this. I've used this in a couple different projects, and it's good for if you just want a medium amount of logic. And basically, you have a bunch of different I/O pins on the device, and then you have a bunch of what they call function blocks, and each of these function blocks contains a bunch of macro cells. And so these I/O blocks just sort of let you grab a signal and wire it on over to here through this switch matrix and connect it over to the macro cells. And so inside of these macro cells, you're going to see something that's basically just a grown-up version of this, okay? And so, oh, wait a second. I apologize. I'm actually sort of missing another slide there. Essentially, within the macro cell is just a huge version of this, okay? And so it's a huge, basically a huge OR gate, huge AND gate and OR gate that you can pick from any of these different inputs. And so you can make, you can implement logic within the function blocks that way. So, and it can use a large amount of inputs. It's basically just a huge version of this. So moving past that, there's a different way of doing things that you can make a much larger programmable logic chip, and that's what's called a field programmable gate array, or an FPGA. And essentially what this is it's a huge matrix of what they call, and there's a lot of different terms used for these, but often one term you'll hear is CLB. Sometimes you'll hear the term slice. Sometimes you'll hear the term LE. They're all sort of talking about pretty much the same thing. But it's a huge array of CLBs, and they're all hooked together in this matrix. And inside each of the CLBs is what's called a lookup table. And inside the lookup table, you've basically got these little bits of memory and a multiplexer, or essentially a switch to select between which piece of memory goes to the output. And essentially, what's done in here is there's just a little piece of memory that literally stores the logic table, or the truth table for whatever function you want. And so it's literally just a piece of memory here, and then you control which bit of memory you're looking at. So in this example, if we turn this one and this one and this one on, then we're looking at this particular value. So does everybody see how that works? So in an FPGA, and we're going to go into a lot more detail about how the FPGA does this. This is just sort of a first look at how an FPGA works. But basically, in an FPGA, you just literally store the value of the truth table into a little piece of memory, and then you control that memory based on your inputs, which are the inputs to your truth table. So the output of the truth table is held in memory, and then the inputs select which little bit of memory that you're going to be outputting. And then there's just a whole sea of these CLBs, and the compiler that I'll show you in a second wires these all together in the right way so that it gets so that the chip becomes the kind of chip that you ask it to be. So FPGAs can store, can hold quite a bit more logic than, certainly a lot more than a small PLD or a CPLD. But the downside of FPGAs is most of them, if you remember, this here is essentially just a piece of memory. FPGAs are, when you turn off an FPGA, it forgets what it was because this is stored in a static memory. And every time when an FPGA is turned on, it goes through and fills up these gates with, fills up these LUTs with all the functions that it wants to store. I'll go into more of that later, but basically, to sort of recap, simple PLD using the sum of products here, the sum of products. A CPLD is basically like within each of these are 18 huge PLDs, and so you can get a lot more logic. And then an FPGA does it in a different way, and rather than actually doing sum of products in there, it actually just has lookup tables that literally just store what the truth table is for a particular bit. And they're able to condense a lot more logic onto a chip, a lot more programmable logic onto a chip that way.
So when it stores that truth table in there, does it tend to store, do we look to generally store just the like what is actually true versus what's false to save on memory? Or do we generally store the whole truth table as a whole?
Well, you have to store the whole thing because it's sort of like you have to have both. If it's just all ones, then it doesn't know where the ones are. It has to store the whole thing to work. But good question. It has to. Essentially, there are two things that this is a good segue to describing it a little bit more. There are two things it stores. It stores all the lookup tables for everything, and then how to wire everything together. That's also configured, and I'll go into more detail about that when we talk about how an FPGA works. So in more detail throughout the class. So this is the type of chip that's on your development board that hopefully you've ordered, and maybe some of you or most of you have already. It's basically a huge. It is just a gigantic amount of logic. In fact, we can, if we go ahead and let me pull up the data sheet for the particular chip that you guys have. So here's actually the data sheet for the FPGA itself. I won't go into all of these details, but let's look at the part that most of you guys have. So I want to say that the basis board has either a 15T or a 25T, and then there's the 50T and the 100T that the larger boards have. And so if you look here, this is the amount of logic cells that device has. So 100,000 logic cells. And then, like I said, there's some different terminology used in here, but essentially, they've got, so they got 15,000 slices. Each slice has 4 lookup tables in it, as well as 8 flip-flops. We'll talk about that as we continue in the course, probably next week. Flip-flop is basically you can store a bit. It's a little register, but we'll talk about how those work. But this is like just a huge amount of logic. I mean, when I was taking this course maybe a decade ago, I think the thing had maybe 10K logic cells. So, it's gotten quite a bit bigger in the past, the past few years. For comparison, a CPLD, basically, so this particular CPLD, it's 18 plus 18 plus 18 plus 18. I think that's 72. Basically has equivalent to only 72 logic cells, and so 72 versus like thousands. So, and that just has to do with how much space when you're making a chip, when you're making silicon, how much space does a little piece of memory take up versus this whole structure. And it turns out that this takes up a lot less space. One of the questions here, does an FPGA have a microcontroller on it? Some of them do, some of them don't. So the one that you guys have for this class, the Arctic 7, doesn't have a microcontroller on it, but they make other parts. For example, let me pull one of them up here. They've got a chip here called the Zinc that it's a lot more expensive chip, but it has, let me see here. This might be a good page to look at. Yeah, this kind of shows it. So this chip has basically has 2 halves to it. It has a whole microcontroller part, or processor part really, and then it has another part that's basically just, this whole orange part is basically equivalent to like the FPGA that you guys have. So you can do a lot of really powerful things with this. You can actually like run Linux up here on this processor part and then have it talk to custom logic that you've built in the FPGA part. So there's other classes you can take here, like 60, it used to be called 676 or 6700 or something now, where you work with chips like this, but pretty cool. The other thing you can do is, remember, for an FPGA, you can make any kind of logic with it, pretty much, essentially. So you could also make a whole microcontroller. You can make a whole processor and implement it within all these lookup tables and interconnects. So if you want a microprocessor, you can make it on an FPGA, and we'll show that by the time we get to the end of the course, you'll be able to make a little tiny processor and of your own design and implement it here with all the logic cells and everything. So, okay, any questions about anything? About, hey, how do we actually implement digital circuits? Variety of different ways, and things became more and more integrated. And then you had programmable logic devices and CPLDs and FPGAs. Any questions about any of that? Okay. All right. So we've gotten here to FPGAs. And so most of you should have your boards by now. So I'm going to go through, and labs are going to start next week. And so let's talk about what we have to do, or what you guys have to do for that. So first thing is you'll have to install what's called Xilinx Vivado. And that is the program that we're going to describe circuits in a language called VHDL. And this is the program that takes what we've described in VHDL and translates it into the configuration for the FPGA. And so it's a pretty big program. I made this little PDF here, Xilinx Vivado install instructions, that takes you through the whole process of installing it. I won't go through everything right now. You can go through this essentially on your own. The highlights really to keep in mind is that this is a huge install. It's about 36 gigs to download and 62 gigs after it's installed. It's what this program is doing is actually like really complex. It's taking just a circuit, a logic that you've described, and then it's having to translate it to fill this huge chip with all of this this whole sea of logic elements and interconnects. And so it's a really complex and, it's a really complex program. They also haven't really, maybe they haven't optimized it as well as they should, but it has gotten better. It is free. Yeah, it's absolutely free. Go ahead and follow the steps here to install it. You want to make sure that if you're installing this on a laptop, make sure it's plugged in. Make sure you set it not to go to sleep. It might take a while depending on your internet connection. And again, it'll use about 62 gigs after you install it. If our lab is on Monday, will it be the following week because of MLK Day? Yes. Yeah. You'll have, for this first lab, you'll have about 2 weeks to work on it. And so, let's say your lab is on Monday, you can start working on it at home, and then on that following Monday, you can go into the lab. But there will be 2 weeks to work on it, we're going to go over things in class and examples in class, and I will, show you some things that'll be helpful. Is lab posted? I'm going to post it either later today or the next day. And yes, the labs are individual. And you'll have 2 weeks to work on it. It'll be due at the end of the month, or essentially first week of February. It'll be the due date will be very, very clearly marked on the top of the lab. So yeah, you can go through and install this. You can follow all these steps. It took me a couple hours, or maybe just over an hour. And then once it's installed, this is the little icon that you want. Has OU confirmed if we can go in person for the labs? Yes. So the order from OU is our lectures have to be online until January 31st, but labs are sort of exempt from that because there's less people in the lab, and you can kind of space out from everybody. You can be more socially distant, and so and if you are really concerned, like you should be about coronavirus, you can work on your lab at home and just come in briefly to show it to your to the TA, to demo it to the TA to sign off on it. I actually have this is essentially, let me pull it up here. This is essentially going to be the lab assignment. I might tweak this a little bit before I post it, but these are the due dates. The due dates are based on which lab section you're in. And at the bottom here, you have to get the TA to sign off on it and date it. And some of this how to generate waveforms and stuff, we're going to go over during next Wednesday. And so you'll have 2 weeks to work on this. Don't worry too much about the first week. I know we got MLK Junior Day for the Monday. You'll have a little bit extra time to work on this. So, and I will post this. Hopefully, I just want to. The only thing holding me back is I just want to proofread it, make sure that it works out okay for you guys before I post it. So, but this is what it'll look like. Okay, so we've got some time here. I'm going to go ahead and fire up Vivado, and I've got my board right here, and I'm going to show you how to just get everything up and get the tools up and running and go through and do your very first example. So, all right. And there are also, I've included a link here on Moodle. There's this VHDL coding for FPGAs, and we're going to use this a lot in this class. One of the other professors, he's been teaching this for over a decade, Dr. Lamoka. He over the years has put together a great set of quick reference and slides and some example VHDL projects. This is a great reference for when you're working on the labs. So will there always be a coding assignment and worksheet due? Yes, to go along for each lab, absolutely. And the other question here I haven't answered yet, is there a final project in this class? Yes. I will give you more information about that as we go. But basically, using all the little bits and pieces. No, the final project will be the final project will be group. You should work in groups, probably groups of 3 or 4. The labs, yes, labs are individual. And some of these questions, if you go to the syllabus, I also talk about, I got everything in here. It says here labs, laboratory assignments, lab work is individual. And then I got some more information here about the final project. So, yeah. Yeah, to answer your question, Cynthia, Paul answered it correctly. You can't really use remote desktop to do the whole lab, because to connect it to the board, you have to actually connect it with a USB cable. And so you can kind of like use remote desktop to sort of compile and synthesize and simulate it, but to actually run it on the real board, you have to physically be hooked up to your board. And so you have to run it locally for that. If you work on a remote desktop, save it to Google Drive, you can open up on the SCCS computers and Laborate. Yeah, you should be able to. I don't see why not. You'll probably, the problem with that is going to be, especially as the labs get more complex, is you're going to work on something and then you're going to want to try it out on the board. And if it doesn't work, you're going to want to change it and then try it out on the board again. You can get a lot of the way just sort of simulating it, but there is this sort of iterative cycle of work on the stuff, go test it out on the board, work on the stuff, test it out on the board. You also work on stuff, simulate it, work on stuff, simulate it, So the remote desktop is there, but it's not the end all and be all. Okay. All right, so let's go ahead and open Vivado. And so Vivado is this little icon here. There's not much Mac users will be able to do from home. Yeah, so it depends on what kind of Mac you have. I use both. I've got a Windows machine and a Mac, and a Linux machine for that matter. And I like Mac for a lot of things. Unfortunately, it's not so good for FPGA development. Two things. One is if you have an Intel-based Mac, you can get VMware Fusion and Parallels, and you could make a virtual machine for Windows and run your stuff on a virtual machine. That's a little slow, but it'll work. I've done that before. It'll be slow inside of a VM, but it could work. If you have one of the new M1 machines, I haven't tested this out yet, and I don't think the driver works for connecting it to the board. So if you have one of the new M1 machines, they're fast and awesome, but you can't run, because basically you need to run in the Intel version of Windows to be able to run these tools. And so M1, you're probably out of luck. Okay. So let's, we got some time here, so let's go ahead and open up Vivado. So I just double clicked it. It's a huge program, so it'll take a little bit to start here.
Professor, I have a question for
Yes.
downloading the Vivado. Do I have to download? So do I have to have Windows on my MacBook in order to run it, or can I do
Yes.
OS?
You have to. You've got to run it in. You can run it in either Windows or Linux. But yeah, if you're on a Mac, you'll have to run it in a virtual machine. Although I'll show you. Will the software work on my Windows PC if it's AMD? Yes, absolutely. My laptop here is an Intel, but my big workstation is an AMD. AMD's great. Yeah, you can totally do it on AMD. Okay. So we're going to go through here, and we will create a new project. And we're just going to call this my project. And we'll go to next. This is an RTL project. And all these steps I'm going through, I'm going to do them again, next week. And the TAs can also help you with this. And if you go to that page on Moodle, let me go here on Moodle, if you go to this VHDL coding for FPGAs, there are a bunch of slides and video that Dr. Lamoka put together over the years. And this also will walk you through the exact same thing about what I'm doing. So, okay, we're going to do an RTL project. We're going to add a couple files here. So we'll create a file. We're just going to talk, or are we doing the labs in person? We do labs in person, or you can do them in person and demo them, or you can work on them at home and then but you have to demo them in person. Okay, so we're going to make one. We're going to call it top.vhd. Top being like the top level design in your project. So that's what that refers to. And then the other file that we're going to, we'll go ahead and, we'll just do that. We'll go to next. And then you're going to want to do this add constraints. And this will, I'll show you where to find these. This is on, if you go here on the Moodle, FPGA board documentation and XDC files. All the docs for all the different kinds of boards you can use in this class are here. And there are these files here called XDC files for each board. One for the Basis 3, one for the Nexus 4 DDR, one for the plain Nexus 4, one for the Nexus A750T, and one for the Nexus A700T. So I went and I already downloaded the Nexus 4 master because my board here is a Nexus 4. So we'll go there, open that, add that to the project. Then you have to select which device you have. And this is, if you look on the lab handout, this will be on the lab handout. So for example, I've got the Nexus 4. I'll sort of put this here at the bottom. Let's see. I'll tell you what, I'll put this like right here. So we'll search here. I've got the X, and there, look at, I mean, there's a ton of them, ton of different parts. XC7A 100, it should filter it, T, and then TC. I'll update this so this has it in a slightly different format, but we've got CSG324 and then 1. So actually, I'll format these a little bit better. But this is the part we want. And if you look actually on the actual chip, hard to see, but that's what's actually printed on the top of the chip. And so we'll go there, select next. And so it makes my project and all that stuff. So now it'll go through, it'll make a project. Initialize your project. Again, this program is like a really beefy program. I'm on a brand new i7 quad-core laptop here, and it's taken this long, so it'll take a little bit to run. Okay, so it is for a lot of these we're going to go and like code like from scratch pretty much, but it has a little thing here that you can kind of make a template for your top level file really quickly. And so we're going to just have 2 ports in this file. We're going to have switches coming in. We're going to do that lowercase. I'll show you why in a second. And that'll be a bus, just a 1-bit bus. And then we'll have an LED going out, and just another little 1-bit bus. And we'll go ahead and hit OK. And just, kind of for this example, that will generate here for us a little skeleton VHD file. And I'm going to just get rid of it puts all these comments here. I'm going to get rid of all these comments just so we can look at our actual VHDL file. And let me ask you guys, did you guys do any of this in EGR 2400? Anything like what I'm showing you now with VHDL or with Verilog? No?
No.
Okay. All right, cool. All right, well, here we are. We're learning it for the first time. And what this is a language, VHDL, that is used to describe chips. It's used to describe digital logic. So like I mentioned this before, it was actually originally developed by the US military for documenting how a chip is supposed to behave. So they'd have, a circuit that they had, and it would go into some piece of equipment, and they needed to know how to make it. They needed to know how to manufacture it. And they came up with this formal language for describing how the circuit works called VHDL. It stands for, the acronym's a little ridiculous. It's Very High Speed Integrated Circuit Hardware Description Language. It's like ridiculous acronym, and this is the language that they came up with. Later, when they were making CPLDs and FPGAs, they basically decided, hey, let's use that same language that we use to just document chips and actually use it to implement it on an FPGA and CPLD. So that's what we're looking at here. And we're going to go over this a lot in this class. I'm just sort of giving you your first taste here of VHDL, but as we learn about the different things you can build with digital logic, I've shown you just sort of the basic gates and things. But as we build up and build more stuff, I'll show you diagrams and things. But we're then going to go and actually make it in VHDL. And that's so we're going to do something like really simple here. So at the top, this is sort of going to be pretty much the same in every file. You're going to have like a library. It includes a library that has a bunch of other functions in it. But just, this guy's going to be at the top. And then every file has an entity. Can I zoom in on the code? Oh, yes. Yeah. Sorry about that. Let's see how to do that. Gosh, let's see. View, it doesn't seem to let me make it bigger. I guess I could change my resolution. It will probably mess up the recording. I'll tell you what I can do is let me open it in Notepad++, and we can edit it there, and hopefully you guys can see it a little bit better. I'll try to get that a little bit. There we go. Nice and big there. Okay. Do I see that okay? So there you go, full screen. Yeah, I could, but I don't think it's going to actually make the text any bigger. It'll do this, but actually, I'll in the meantime, for right now, so here we go. Here's our VHDL. We've got and actually, if we just go ahead and save this as a, top.vhd, it'll do our nice syntax highlighting here. So we've got, this describes the inputs and outputs of a particular unit. And so this is the very top level design. So in the top level design, what I'm describing here are just literally the pins of the FPGA. So one goes to a switch. It comes from a switch. It's an input to the FPGA. And then we have an output here going to an LED. And so that's in the entity. And this is in the port description. Then it says, under here, architecture is, and then under begin, this is where we write like what we're going to do. And so I'm going to do real simple here, LED 0. So the lowest bit of the LED is just literally going to get what is on the switch. Very, very simple program. So literally all we're doing is input pin of the FPGA. We're just literally going to set the output to whatever the switch is. So simplest possible VHDL program. So let's go ahead and take that. I'm going to paste it into here and save it. Now, how do we know what names we're allowed to use in our top level? Okay, how do we know that like switch goes to a switch and LED goes to an LED? That's what this constraints file is. So let's go ahead and open this. And I'll tell you what, I will copy this also to Notepad++. Oh gosh, that looks terrible. Let's see. Okay, you can kind of see what's going on here. Everything in here, this is what describes which pin of the FPGA, what name you call it in your VHDL program, okay? So each line here, or each section, so like this is a section, for example, talks about the pin for switch 1. This one here, or excuse me, for switch 0. This section here talks about the pin for switch 1. And it says what, because this is how the FPGA knows about the pins. The FPGA's pin numbers are U8, U9, R7, R6, but we want a nice friendly name like SW0, SW1 for switch 0s for switch 1. So yeah, so switch 0 means switch 1. Yeah, everything is like 0 index, right? And so switch 0 is the first switch. If you have 7 switches, or excuse me, if you have 8 switches, they're going to be switch 0 to switch 7. It's just the way it is. It's all 0 indexed. And And we'll go through a lot of examples to really get that clear. But yeah, switch 0 is going to be the first switch. And if you look on the board, it's probably hard to tell on here, and it's actually probably reversed, but it's actually printed on the board. SW0 is actually printed on the circuit board, which you'll see. And so the pins that we're going to use in our design, we actually have to go here and uncomment them. Okay. And when you do that over here, it will color them, that they've been uncommented. We're sort of enabling this pin on the FPGA. And then we're also going to use LED 0, so we're going to go and uncomment that as well. So everybody see what I did there? So here's switch 0, I uncommented. What these are is this says SW0 goes to, it's a package pin, that refers to the pin on the actual package of the FPGA. It's called U6. And then this IO standard says like what kind of voltage that pin is at. You don't have to mess with these, but just uncomment them, and then it'll use it in your design. If you have these commented and you try to compile, it'll get like 2/3 of the way through, and it'll say, I don't know what SW0 is. What are you talking about? So, you got to make sure that those are uncommented. So, okay, so those are uncommented, and we've got our real simple example here, and we are going to go ahead now and we're going to run. There's a couple different steps here: synthesis, implementation, and generate bit stream. And so we're going to go through run synthesis, hit OK. This will take a little bit. While it's going, I'll describe what it's doing, and you can see it going through a bunch of, crazy stuff here going on in the log. So what it's doing is we've described very, very simple logic here, and it is analyzing what we've described and figuring out how to take this blob of lookup tables and interconnects and fit what we wanted to be on the chip, And so this is a pretty complex process, takes a while. And actually, if we look here at, it takes quite a bit of, I've got a lot of memory in this machine, and it's using almost 13 gigs. I think as it gets towards the end, it uses almost 16 gigs of memory. And so I think actually more in the implementation part. So some of this might just be, I have a browser open, but it will use close to 16 gigs and a lot of your, CPU too as you go. Although a lot of this might just be the call. Okay, and then it says synthesis completed successfully, run implementation. So actually, to be a little bit more descriptive, in synthesis, it's taking the logic you've described here, and it's figuring out what all the gates are. It's figuring out, okay. And even though this design is really simple, the software just analyzing it, and there's sort of a certain minimum amount of time it takes to do it. And then in implementation, it's actually taking that and mapping it onto individual pieces of the FPGA. And so we've got implementation is running here. You'll see, CPU, Vivado here taken up and using north of 3 gigs. I think a lot of this maybe is just caching things. Anyway, I show this to you just to say, like, don't be surprised if this takes a while, depending on your machine. And it's still running. You can see here in the corner this running route design. It's you can see it spinning there and kind of going here through the log. Unfortunately, it doesn't. For most of the process, it doesn't use, like, if you have like 16 cores in your machine, it really only uses 2 of them for a lot of the process. You see they're multi-threading enabled for using a maximum of 2 CPUs. Now, one thing you can do here, it's kind of interesting. You can go open implemented design, and it's really not going to show much because our design is so simple. But you'll see a little bit behind the scenes of what it's actually doing. Second. So, like, this is a representation of the whole chip. And if we zoom in here, these are all the little logic cells inside the chip. Over here, you've got your I/O blocks and a bunch of other different kinds of blocks. And here you can see where it's chosen to map some of this logic. It's literally only, it's hardly using any logic. It's just using an input. It's using 2 pins, basically, an input and an output. But as we make more complex designs, you'll see it populate up. Here's our little lookup tables. And actually on this device, it is a 5-input lookup table, which can store, should be what, 32, it basically stores 32 different, 2 to the 5, to the 4 would be 16, and so 2 to 5 should be 32. So this is a lookup table, and then zoom out, and those are all the lookup tables on here. It's pretty crazy. Okay, so we run implementation, and then we're going to go here and do generate bitstream. Hit OK. And then hopefully I did everything right, and we're not going to get any errors. If you do one little thing wrong, it could error out at any of these steps. But I went through, and this simple example should work. And we can kind of see here, it's doing more stuff, and then it's running. It says running write bitstream. So it actually should be programming it on the board. It's taking a second here. Again, it's a pretty beefy program. There's a button to test your code debug. Yeah, okay, so I'll show you that. So it made the bitstream now, and then what we can do here is we're going to select Open Hardware Manager, and then here we go, it says no hardware target is open. We're going to go Open Target, Auto Connect, and if everything's connected just right, it should go and run it on the board. Well, it'll actually connect, and then I think it gives me a button here that says program. And so, again, it's a pretty big program here. Okay, and then we go program device, and then it'll automatically grab the bit file that we made. We go here, program. It says programming the device. Okay, and now as I've done that, as I was doing that, there's a little LED on here that says done, and that LED turned on. You can see that there in the camera. Okay, and then that LED right there is our first LED, and you can see as I move the switch up and down, that LED turns on just like we programmed. Okay, so and yeah, that LED is the one that goes off and on. Like if I go and if I program it again, go program, and you'll see that go off briefly, and then when it's done programming, that LED turns on, and then we got our little program there. One thing you'll notice is if I go and program it again, you'll notice my LED went off here. My test LED went off in addition to that LED. So it takes a second to program, but then once it's programmed, it's got exactly what I asked for. So we're just about at the end of time here. For those of you who want to just stick on the call just for like maybe 5 more minutes, if you want, I'll go through and I'm going to do one more example where I actually do like an AND gate using 2 switches. So if you have to go, there's a recording of this, so you'll be able to watch what I did. But I'll just do one more example here. So,
Professor,
yeah.
Before you go for next class, when you post your when you post the notes from like the last class or like your PowerPoints, can you post them before you go to or before you start the class so that way that at least it can kind of take notes over top of it?
Yeah, that's yeah, absolutely. I'll make sure to have that posted ahead of time before the next class. I'll try to post it at least the morning of class so you can log in